Welcome to EE 597 on Monday, August 1st, 2016.
Okay, so just to resume from the last class, we talked about back pressure scheduling and back pressure collection protocol. And the first thing I want to do is just clarify again what is the difference between these two sets of things. The back pressure scheduling is sort of an algorithm that under idealized assumptions such as global synchronization, central monitoring, solving NP-hard, max weight, independent set, problem, infinite buffers, etc., guarantees throughput optimal performance. And I've said this a couple of different times. What's the guarantee it provides is that you have a set of flows and you have constraints over which links can be activated. It guarantees that if there's any algorithm that can schedule the set of flows over the links without causing instability, that the max weight algorithm can do that. The back pressure collection protocol, or BCP, is a practical protocol for collecting data from nodes in a wireless sensor network. Okay, that is inspired by back pressure scheduling and removes a lot of the idealized assumptions. Okay, what does it remove? Well, in particular, BCP does not require time sync. Unlike back pressure scheduling, which is like a time division multiple access scheme or TDMA scheduling scheme, it is based on uses randomized access. And it uses this randomized access from the underlying CSMA layer. In other words, it simply doesn't try to figure out how to schedule these links to be without interference with each other. It lets the link layer, which is implementing a wireless CSMA protocol, take care of that issue entirely. And therefore, it focuses only on letting nodes make forwarding decisions. It doesn't assume ideal links or doesn't assume perfect quality links, and hence the ETX term in the weight calculations. It also simplifies the problem to focus on what's called a single commodity flow. Okay, i.e., all data goes to one sink. So you're not maintaining different queues for different flows. And in fact, you could generalize it so there's more than one sink, but in some sense, you shouldn't care which sink the data gets to. So it's not like you're going to make copies of your data to go to different sinks. You're sending the data, and so long as they get to some sink out of the network, it's pulled out of your network, then you can generalize it to that setting. But it doesn't handle multiple unicast flows. So that's one simplification. Generalizing to handle more flows will require maintaining additional queues. One for each flow. And of course, you could do that. There's nothing wrong with generalizing BCP to implement that capability, but intuitively from a performance standpoint, it may not do well, because if you have one queue for each flow, you have n nodes, and any pair of them want to communicate with each other, you may have n squared queues at each node in the network, and that doesn't scale very well. Like if you have 30 nodes, that's 900 queues at every node in the network, and that's just not practically something that you're likely to be able to implement. Does not assume infinite buffers, and something I didn't talk about in the class but is in the paper, which I just remembered we didn't post a link to, but we will. And if you don't see it there, you can just Google for back pressure collection protocol. The protocol also builds in ways to make sure that if your total number of packets goes above the available queue size, that you can virtualize some of the packets into just numbers and still store them within the network. But of course, then you'll suffer some packet losses as well. And then one other fact about the back pressure collection protocol, which I mentioned last time, is it uses last in, first out to serve packets at each queue instead of first in, first out. And this improves the delay, particularly at low arrival rates. But, and there's a trade-off, means that some trapped packets are not delivered, and people, actually students at USC, have come up with variants that can be virtualized. So these trapped packets can just be virtualized, so are not real data carrying packets. Okay. Or alternatively, you send dummy packets at the beginning of your route formation phase, which are just intended to help create this gradient using these packets that stay trapped, and from that point on, you're using LIFO to move your data packets as quickly as possible through the network. I did mention some properties of BCP, and that's in the homework assignment as well, which is that at steady state, BCP establishes gradients pointing to the sink node, and specifically if ith node has shortest ETX path of cost, let's just call it CI, then the number of packets in the gradient, in the queue, establishing this gradient, will be V times CI. So let me clarify what we're trying to say here. So recall BCP works as follows. So BCP says compute this gradient Wij, which is Qi minus Qj minus V times ETXij. Okay. So if okay, and then find J star that maximizes Wij, and if Wij star is bigger than 0, then send next packet from I to J. So this has two implications. First of all, if Wij star is less than equal to 0, don't send packets. Right? So if you have negative weight to all of your neighbors, it means that they should be sending data to you. You shouldn't be sending data to them. And as you can imagine, if this were to persist at a node for a long time, that would be trouble, because they will send you packets and you can't send them packets. That means your queue is going to keep growing. Right? Well, this will happen to the sink at all times, because to the sink, everybody should be sending their packets. It shouldn't be sending its packets to anyone. It's the sink node. And there, the weight will be negative or equal to 0, and that's fine. But it may also be that during some moments of high congestion or interference, some node temporarily is unable to send packets because it's too congested around it, and actually gathers packets, and its queue will start to build up. Eventually, though, its queue will start to build up to the point that Qi term starts to get large, and that will make the weight positive, and then at that point it'll start to send packets out again. So basically, even if temporarily it happens, so basically may happen temporarily at other nodes due to local congestion, and that's fine. That's part of the design of BCP. On the other hand, it will always happen at the sink. Right, so obviously the sink node, because its queue is always 0, it'll always have this term being negative. So what is the steady state behavior we're talking about? And let's look at a couple of simple examples. So let's take one example. Here's a sink. Here's node 1. Here's node 2. Let's say the ETX on this link is, 2. The ETX on this link is 3. Okay, so this is ETX values. So what I mean by steady state really is that imagine some packet shows up at one of these nodes. Say maybe a packet shows up here, right? So if a packet shows up here, it has one packet sitting in its queue. It's not going to move anywhere. Why is it not going to move anywhere? Because at that point, Q2 minus Q1 minus 2 times 3 would be equal to 1 minus 0 minus 6, which is negative 5. So in this situation for this node, with respect to the only neighbor that it has, the weight is negative. So it's not going to move any packets anywhere. This node, which has 0 packets at this point in time, of course, is not going to move anything anywhere. It has nothing there. Imagine another packet shows up here. So for this node, there are 2 possible neighbors. It could potentially send the packet backwards. You would say, why would it ever want to send its packet backwards? Again, that's possible in BCP. In this particular example, it won't happen because the next neighbor over here is the sink. But if you had some other node between it and the sink, and that node had a really high congestion, temporarily BCP might actually send its packet away from that congested region and have the packets wait somewhere else until the congestion eases, and then they'll flow back. That could happen. So at any rate, all the possible neighbors would consider in the calculation from this node onwards, it would look for this reverse link, which would have, so if you look, for example, at this situation, Q1 minus Q2 minus, again, the ETX on this link being 3, let's assume in both directions. Even if it had a packet 1 and 1 is 0, this would just be minus 6, so it's also less than 0, nothing's going to move. In the forward direction, it does have more packets in its queue than the sink does, but the calculation we're doing has to take into account an additional ETX weight of 4. So in this direction, Q1 minus Q sink, if you will, minus 2 times 2. This is 1 minus 4, which is minus 3, and that's also less than 0. So in this case, even having one packet here, it's not going to move that packet to the sink. Okay, so that's this gradient notion we're talking about, is that it has to overcome that ETX value before it will push a packet to the sink. What's the intuition? The intuition is that if we consistently did this everywhere in the network, we wouldn't move packets unnecessarily, particularly over links which have very high ETX values. So this creates a barrier to moving packets over high ETX links. Okay. In this case, it's not obvious why you should do that, but in the context of the overall network, that's the reason why this second term is present. But what's going to happen now is if I add packets, you are looking for the condition under which the network still remains kind of in equilibrium, in the sense that no packets are moving from any of the nodes and changing the current number of packets that you have. So if you have just these 2 packets sitting in the queue, nothing else shows up, they will just sit in those queues doing nothing. Okay? So the steady state notion is basically, so the steady state, okay, if a number of packets arrive in a burst, let's say a large number of packets arrive in a burst and are emptied out, which packets remain where? Which packets remain, or really, how many at each node? Okay, that's the question that we're asking when we talk about the steady state. So if I had only 2 packets, they arrive and they just sat there, they're going to sit there forever. Okay, but what if I had like 1,000,000 packets show up at these 2 nodes, and now I just wait and watch the process? So intuitively, what's going to happen if I have a very large queue here and a very large queue here? Let's just assume that they're the same number of packets. Well, if they're the same number of packets, there's ETX gradient between these 2 of 6, that unless there were 6 more packets over here, then this node, nothing's going to move. But between these 2 nodes, now the gradient would be far more than the 4 it would take to move packets on this link. So long as there's more than 4 packets at this node, it will move to the sink, right? So if you have 1,000,000 packets, the first four, a first packet will move down, the second packet will move down, the third packet will move down, and so on. And then at some point, you'll find that this node has 6 packets less than this node, at which point some packet from here will walk over, right? And then, again, this node will start emptying, will basically continue to send packets to the sink. This node, whenever it has 6 more packets than this node, will send packets to this node. And this will keep happening until eventually the queue at this node drains all the way down to no more than 4. Because if it has any more than 4 packets, it will move them. But when it gets down to 4, it won't anymore. And similarly, this node, if this node has 4 packets, will keep sending this node packets until it comes down to 10. Why is that? Because for any number 10 and less, the Q2 minus Q1 minus 6 will not be positive. So for it to be positive, it has to have more than 6 packets than whatever's in this queue. So if this is 4, this has to have more than 10 packets to send. So at steady state in this particular network, what we're going to end up finding is the sink will get most of the packets. This node will end up with 4 packets. This node will end up with 10 packets. Okay. And the sink has, of course, 0 always, because that's the definition of the queue at the sink. So this is the steady state queue occupancy for this particular network, right? And the reason it's a steady state is that at this point, there's no more movement of the packets. This node will not move any packets backwards because it's a negative queue difference. This node will not move any packets because the queue difference is positive, but it does not overcome the ETX difference of 3. And similarly, this node doesn't move any packets because of the ETX gap being now 2. Okay? But I said something a little bit stronger a couple of pages above. I said at steady state, what BCP is going to do is it's going to establish these gradients pointing to the sink node. So by gradient, we kind of mean this decreasing number of packets pointing towards the sink node. And if the ith node has the shortest ETX path of cost Ci, the number of packets in the queue establishing this gradient would be V times Ci. So what is V? V is the weight with which we're combining to the ETX. So BCP says Qi minus Qj minus V times ETX Ij. Here we're assuming, so if V equals 2, well, what is the shortest ETX path from this node to the sink? Has an ETX of 2. 2 times 2 is 4. That's how many packets it has sitting at its queue. For this node, you have a total of 3 plus 2, 5 is the shortest ETX path from this node to the sink. 5 times the V value of 2 is 10. That's how many packets will sit at the sink. Okay. So the claim here is that if you were to compute the shortest path according to ETX multiplied by V, that's how many packets will be sitting at your queue in steady state with BCP. So we won't prove this property, but let's see the implication of this property for a network where there's more than one path for some node. Let's say this is the sink. Let's just say 1, 2, 3. Okay. And let's just say ETX values are 1, 2, 4, 6. So the claim is that for this node, what is the shortest ETX path to the sink? It's 1. That at steady state, it will have a queue size of 2. Okay, let's call it Q steady state. And this should have node number 2 because it has so these are ETX values. Let me just clarify. The steady state queue should be assuming V equals 2. Why do we choose V equals 2? Empirically, we found this to be a good value for BCP, but it could be any number. At this node, because the shortest ETX path is 2, we'll have a Q steady state of 4. This node has 2 possible paths to get data to the sink, either this path, which is 6 and 1, 7, or this path, which is 4 and 2, 6 ETX. So the claim is that at steady state, this would have a queue size of 12. Okay. So I won't prove it in general, but let's at least understand why this is intuitively a reasonable scenario to have happen. Is this even true? Actually, is this even true? Let's see. So let's look at this node. So certainly if it had less than 2 packets, they're not going to move to the sink, right? Because it won't be able to transfer them because Q1 minus Q0 minus 2 times the ETX for it, this has to be bigger than 0 for node 1 to move a packet, right? Well, Q0 is always 0, which means that Q1 minus 2 must be bigger than 0, or Q1 must be bigger than equal to 2 for node 1 to move a packet, right? Therefore, the steady state Q at 1 is equal to 0, is equal to 2. Right? Any number less than this, it won't move. Any number more than this, it will move, right? In the other direction, it's going to be, if Q1 is bigger than 2, actually not greater than equal to, it actually have to be strictly positive, right? So, for any number bigger than 2, a packet would have moved. So at steady state, you would never see more than 2 packets sitting in this queue. Okay? And by the same line of reasoning, the steady state queue at node number 2, right, will have to overcome a gradient of 2 times 2, which is 4. So for any number bigger than 4, a packet would have moved, which means that at steady state, it's actually equal to 4. Okay. So now let's imagine this network. I have 2 packets sitting here, right? 2 packets sitting here. And then I have this node number 3 has its own queue size. And in this direction has an ETX of 6. And in this link has an ETX of 4. The question is, how many packets can I have before something will start to move? Okay. So, sorry, here it should say 4. So, if Q3 minus Q1 minus 2 times ETX of 3 to 1 is bigger than 0, then it will move a packet. Or if Q3 minus Q2 minus 2 times ETX 3.2 is bigger than 0, in either of these two cases, Q3 will transmit, right? A packet. And if this one's true and this one's not true, it would send a packet to this one, and vice versa. If they're both true, it will send a packet to whichever one has a higher weight. Okay. So, under what condition would this hold? So let's try that out. So we know the values for Q1 and Q2 at steady state. So we're trying to figure out what Q3 might be, but sort of at steady state. We've determined that QSS2 is 4, QSS1 is 2. So Q3 minus 2 minus 2 times ETX over here is 12. Okay. Or Q3 minus 4 minus 2 times the ETX here is 4, so 8. So if either of these two conditions was true, the node will transmit. The first one is saying Q3 minus 14 is bigger than 0. The second one, right, so this is sort of case 1, this is case 2. So this one's implied by case 1, and case 2 implies this. So basically, if the queue satisfied either of these two conditions, we're going to move a packet. Of the two conditions, the stronger condition, or the condition that is guaranteed to satisfy both of them, is this one. Right? So if Q3 is less than 12, or less than equal to 12, neither holds. Okay? And Q3 bigger than 12, the second condition holds. And node 3 will transmit, right? So therefore, any number for Q3 bigger than 12 cannot be in steady state. At any number bigger than this, assuming the other queues are in steady state, you will push a packet out. Which means that at steady state, it has exactly 12. Okay? Which is consistent with the fact that the smallest ETX path for node 3 is this path, because over here it takes 7, over here it takes 6. Okay? Note, shortest ETX path for node 3 has ETX equal to 6, and then V times 6 equals 2 times 6 equals 12. So it's not a coincidence that these two numbers come out the same. Okay. And you can actually prove this. You can almost see here how you might construct a proof of the statement that I made. The proof would be by induction on nodes from the sink onwards. So for the sink, the distance is 0, the queue size is 0. For the node that's closest to the sink, it will send its packet so long as it's got V times whatever its ETX to the sink is. And then from that point on, you can basically construct an argument by induction that says that if everybody going ahead of you has that condition hold, then you would pick whoever gives you the shortest ETX of those, and then your steady state queue would be determined accordingly. So what this means is that the gradient on this particular network, if you were to kind of imagine it in steady state, looks like this. So we said Q1 has 2 packets. This is 4 packets. This node has 12 packets. Okay. So additional packets beyond and above and beyond the steady state. So if you had an initial set of packets that went through and established this gradient, from this point on, if node 4 has a packet, it will just go directly to the sink. If this node has any packet, it will go directly, depending on whichever one has the steeper gradient, depending on how many packets you have here, and the particular packets you have here, they will move in the corresponding direction. So the default route, in some sense, that you get with BCP is the shortest ETX path, right? Sort of if all nodes are at steady state except one node which gets, say, an additional packet. So imagine this is the steady state and node 3 got an additional packet. How that packet will get to the sink is to follow exactly along the shortest path through the network. Okay, this packet will flow to the sink along the shortest path. So this is the sense in which BCP actually behaves like a shortest path routing protocol. But it doesn't do this all the time. It only does this when all the queues are sort of in this steady state configuration. In a real system, there are packets arriving at different nodes at different times. And if this was the shortest path for this node 3 to take, right? So this is maybe the shortest ETX path. But at the current moment, there's a lot of packets arriving at this node. Then BCP will not try to force the network to take this path. Because there's a lot of packets arriving at this node, the queue size for this node will grow. And BCP will notice that this queue is large and will send the packet along a different route instead. So in other words, when there is congestion in the network, it diversifies the paths. Okay. So when there is congestion, other paths are followed. Okay. So that's really the intuition behind what BCP does, is it sort of can behave like shortest path, but if there is a lot of congestion which happens when the traffic increases, then it will take into account the current queue state and try to distribute traffic as equally through the network as possible. In fact, mathematically, you can show that what backpressure scheduling tries to do is it tries to make all the queues in the network as equal to each other as possible. So one reason why you want to move packets away from one direction is because this queue is already getting pretty large, so you want to put some more packets somewhere else. Okay. And if you didn't have that ETX term, what backpressure would try to do is make everybody's queue as close to each other's value as possible. Of course, the sink will always have zeros. So that'll keep pulling the packets out of the network. But other than that, it sort of tries to make things as load balanced as possible. Right? So you can, think of that for load balancing. Okay. So that's really sort of the reason why back pressure scheduling gives you benefits. So I wanted to mention, and I forgot to send an email about it, but today I have an extra pre-taped lecture from 3 to 4 p.m. in OHE 136. It's a pre-taped lecture because I am not here on Wednesday. So we don't have a regular class on Wednesday. So no. So in fact, that 3 to 4 session will be our last lecture session for the semester. Your assignments have been posted online. It is due Friday. I also asked the TA to post sample final exam questions. So you can take a look at those. The exam on Monday, August 8 in class. And basically we'll cover everything up to today's tape lecture. Yeah, after the midterm. So it's not cumulative. Okay. In terms of the topics that the exam will cover, some of which, of course, we've already covered, and the rest of which are in today's lecture and the pre-tape lecture, as well as in your homework assignments. So we did cover some sleep cycling for medium access. I think that was the last MAC topic I touched on. We touched on any path routing. Sorry, before that, ETX as a metric, right, what it is. We've talked about cooperative broadcast. Back pressure scheduling. And definitely between the homework assignment and the problems in the final exam sample questions, you'll see the type of questions one can ask about any path routing and back pressure scheduling in particular. Back pressure collection protocol, which is what we've been talking about now. And there's some questions related to that as well. There is a topic that for reasons of time, I don't cover in the lecture, but both the assignment and the sample midterm, you're asked to read and browse through the AODV paper and answer a question about the basics of AODV and how it works. So basically, picking that up on your own, and that's something you are responsible for. So definitely, strongly recommend read the paper. Okay. And for the exam, just as last time, you can bring in any printout or written notes. I would recommend bringing a printed copy of the AODV paper. In addition to this, we're going to talk coming up about, intermittently connected mobile networks. And a little bit about TCP. There's two sets of issues. One is called loss notification and fairness. for wireless. Okay, and at least some hint at sort of alternatives to TCP for wireless. I think I might end the class there. So we still have a little bit of ground to cover in the rest of this class in the 3 to 4 sessions. So that's what I'm going to focus on now. So let's talk about intermittently connected mobile networks. And so the motivation is, examples of these would be like mobile device, P2P connectivity, or like in vehicular networks we talk about them. So the basic idea is that you have a set of nodes that are, moving around whatever environment they're in, whatever setting this is. So the nodes might be, are humans or cars or animals, actually. There were some very interesting research studies where they put radio tags on wildlife, including, I think it was zebras in ZebraNet. And whenever, they have these tags, they're going wherever they want in the environment. Whenever two nodes are in range of each other, okay, they are mobile, and their mobility might be quite random or predictable in some cases. So, for example, if they have some schedule for where they're going, they may be buses on a street, and you have or trains in a train track, and you have a very specific idea of how they're moving, or they may be unpredictable and random. In either case, they're mobile, and two nodes can connect to each other whenever they are within range. So in the ZebraNet study, for example, if two zebras happen to get within a few tens of feet of each other, they're able to talk to each other. We did a similar study here at USC many years ago. We basically handed out a bunch of modes to a class of freshmen to carry around with them for a week. And whenever two students would meet each other, they would log the ID of the other node and log how long they were in contact with the other node. So sort of who meets whom, when, and for how long. So I think I might have, in fact, a video from that study, which I can try to dig out. I'm having some problems here with the mouse control. Okay, let's see. Not sure why. Okay, let's try that later. Okay, so they're potentially mobile. And so what can you do to deliver data in this setting? So one key observation here is that the network graph is not necessarily connected at any moment in time. Okay. So we say a graph is connected if there exists a path between any pair of vertices. Right? If you have a network which kind of at any given moment in time just happens to look like this, that you have a bunch of contacts between nodes that are near each other, but there's no way in that moment in time to get data from here and get it to this node. So maybe the only way you can get data from here to here is this is the snapshot for now. A little while later, maybe this node moves somewhere, this node moves somewhere. Then they have a link between them, and then they can transfer the data. So for this type of a network, because the network is not always connected, standard shortest path routing, broadcast routing, the standard back pressure, scheduling, etc., will not work. At least in the sense that in any given short duration of time, you simply can't get the data to where it's needed. So instead, what might be needed to be done is called store and forward routing. So the idea of store and forward is nodes might collect pieces of data that they are intended for other nodes in the network. They don't forward them right away. They store them. They move them around. When the right opportunity presents itself, then they forward them. So the simplest possible mechanism for such a network is just called wait and deliver. Okay. So the idea is very simple. Node A has data for node B. If A, B are in range, A transfers the data. Else, A waits, storing the data. Okay, so it doesn't get any simpler than this. You have data to send, you wait till you meet them. Okay, we do wait and deliver routing all the time in our lives. You're wanting to tell something to someone, actually not all the time in our lives anymore. Back when I was a kid, the way you got data to other people is you waited till you met them in person. When you met them in person, you told them what you had to tell them, right? That's wait and deliver. And in fact, in some sense, that is a good model for what we're describing here. So there's not enough remote communication capability. You have to kind of incur latency in order to communicate data to who you want, right? So incurs latency. Now, this mechanism does incur latency, but clearly one benefit is that it's sort of efficient in terms of number of messages, in terms of number of transmissions. Because you're waiting till you actually encounter the destination before you will hand over the data, you're not expending one more transmission than you need. There is no relaying of traffic, there's no forwarding, there's no copying, there's no flooding, there's nothing. You just hand over the data. Okay. So it's as efficient as it gets as far as the number of transmissions is required. Maybe energy is something that that matters. From that perspective, this is very good. So that's good about it, but does not work Why is that? Why might it be that wait and deliver just simply doesn't work? You might have to wait forever because you never get in range of the destination. It may just so happen that these two particular nodes, the way they move around, never actually come into contact with each other, right? In particular, if A and B do not meet. Or they may meet, but meet infrequently. The problem here might be you simply don't have enough bandwidth. So maybe that you meet them for a very short duration, but the amount of data that you have to convey to them is much larger than the time of the encounter. So even when you do meet, you can transfer some of the content, but not all of it. So you hold on to it for the next meeting, but by the time the next meeting happens, you got even more data to tell them, and so you never got around to telling them this first piece. And so if the rate at which you meet them, the amount of bandwidth that you have available when you meet them is smaller than the amount of data that you wish to communicate, then you basically have an unstable queue. You have data arriving faster than it can be delivered, and that's going to mean you cannot communicate. So even if you do meet, but you meet infrequently, this could be a problem. So that allows us to, or that pushes us to consider alternatives, right? So here's one alternative. This one is called epidemic flooding. Every node I, upon contact with a node J, makes a copy of all its stored packets and transmits them to node J. Let's take the simplest setting. There's only one packet in the network that needs to be communicated. Here's node A, and it wants to communicate it to some node B. And it's going about its day. It meets some node number 1. That message that it wants to communicate to B, which it's storing in its local storage, this message M, gets copied over to node 1's buffer. Okay. Then node 1 doesn't quite meet B yet, but maybe it meets some other node 2, and when it has that interaction, it copies this message over to node 2. Meantime, node A met some other node 3, and these diagrams are really suggestive more than illustrating anything particular, because every node's kind of mobile in the area. But at some point, node A meets node 3 and makes another copy of its message. So the point is that you can make as many copies as you want. Every time you meet someone, you make a copy. If you want to add a little bit of efficiency in here, you don't make a copy if they already have it. Maybe there's a way for you to check, do you have this? If you don't have it, let me hand it to you. So you do this, so this is called flooding because you're basically making copies of this packet and you're spreading it wherever you have a contact. And then maybe what ends up happening is that node 3 actually eventually meets node B, and by the same process it will deliver that packet to B, right? So node B's eventually going to get a copy of it by meeting somebody that has a copy. It doesn't have to be node A directly in this case. It could be any of the other nodes that had some interaction with some other node that had the packet. So it is a process that's somehow random, if you will. If the mobility is random, exactly which node delivers the data to B would be a function of which nodes, as you backtracked all the way, happen to be the earliest way for the data to get to B. So some observations. So first of all, if there is any way to get the data from A to B, flooding will deliver it, setting aside bandwidth limits. So there is one case when it won't work, which is that the data itself is so large and every encounter so short that copies don't get made. But assuming you have enough time to do the copying, there's not so much data, then if there's any way at all that the data could have spread to B, it would spread. Because every transmission opportunity was taken advantage of, right? So if there's any way at all that this can happen, so at least it deals with one problem we identified with wait and deliver, which is that it doesn't always work. If they don't meet or they meet infrequently, it can deliver. Well, flooding has a nice property that if there was any way to deliver, it'll deliver. If there's no way to deliver, of course it can. It's kind of similar to what we said about Maxwell, but if there's any way to deliver, it will deliver. Well, what other things can we say about it? In fact, it can deliver in fact, will deliver with lowest possible latency. Okay? And that's pretty remarkable because it says of all the possible ways in which you could have delivered data from A to B, whichever was the quickest set of combinations, like maybe A to 1 to 2 was not the shortest, but A to 3 to B was the shortest. If that was the shortest path in their mobility, which you didn't even know in advance, it will deliver along that path. Okay? It's because it delivers along every possible path in some sense. And if there's an earlier path that could be taken, it would have taken that path. Okay? And so there is no low latency path that there exists that is, I was going to use the word causal, but let me explain. So for example, maybe 2 meets B before it meets 1, right? And maybe technically that meeting between 2 and B was earlier, but that doesn't offer you a causal path from A to B. The causal path has to be the meeting between A and 1 happens before the meeting between 1 and 2, and that meeting has to happen before the meeting between 2 and B. Right? So if you look at the sort of shortest causal path from the source to the destination, the flooding will take that path for sure. Because whenever those meetings happened, packets were exchanged. Okay? I.e. along shortest causal path. Okay. All right, so now we know something more about it. So we know that it is robust in some sense, right? It has low latency. So this is flooding. And let's compare it with wait and deliver. So this is maybe not robust, has high latency. And the high latency for wait and deliver is it could take a long time before you meet the final destination. With this one, the shortest way possible you will meet it. On the other hand, wait and deliver had the benefit of very high efficiency, right? Or, in terms of number of transmissions being as low as possible. And here it's the opposite. It has sort of low efficiency in terms of number of transmissions. In fact, it incurs the highest number of transmissions possible. Because every node in the network is going to get the message, and every time it meets any other node, it's going to copy a message. So every possible transmission opportunity being exploited, on the one hand, is good for latency, on the other hand, it's bad for efficiency. So this is sort of a trade-off, right? Between latency and efficiency. And in fact, if the data rate is high of arrivals, the low efficiency of flooding means a lower throughput. Why is that? Because every time you meet someone, you have to make a copy. And making copies is taking up time. So if you have limited bandwidth and a lot of data coming in, if you're spending a lot of your transmission times making copies, then that's eating into your available bandwidth. So the total capacity of the system, if you will, is getting reduced by all of this extra copying activity happening in the network. So from that sense, it could be a latency throughput trade-off as well. Okay, so what researchers found when they were looking at this trade-off is that maybe there's a way that we could improve by picking something that isn't quite as extreme as wait and deliver, but isn't quite as inefficient as flooding either, but somewhere in between, or maybe better yet, a way to tune between these two mechanisms. And such a system is called spray and wait, such a protocol. And in fact, this was developed right here at USC. Professor Sunis and Raghavendra, who are colleagues of mine in the EE department, were co-authors on this paper. And Akis Spiropoulos, who's the first author of the paper, he was a PhD student at USC and now a faculty member in Europe, worked on this protocol and actually a number of other papers in the delay-tolerant networking area. So their scheme works as follows. So initially, the source node has a certain number of copies of the packet. And I put this in quotes because they're not so much copies as the total number of copies it's allowed to make. So let's just say that's the number k. At each encounter, a node that has the copies, has, let's say, if we call this capital K, let's say lowercase k copies, hands over half of the copies, so k over 2 copies, to the encountered node if the latter has no copies, so long as k is bigger than 1. If k equals 1, no more copies are made, let's say, by the node. So what does this look like? Let's kind of try and imagine this. Since we're doing this kind of binary splitting, so you start with a certain number of copies, you give half, you keep half, you give half of that again, you keep half of that, you give half of that again, you keep half of that, and so on. It's like a binary tree. It's going to describe who has how many copies at any given time. And this number k, for doing all these binary splits, it's meaningful for that big K to be some multiple of power of 2. So let's just say k is 16. Okay, so the source node initially has 16 copies. Okay, so say the source node is A. So let's just say A meets node 1, and when it meets node 1, then A will have half of these with itself and hand over half of them to node 1. So then after this, node 1 will have 8 packets. So initially A had all 16 packets. After this, node 1 will have 8 packets, node A will have 8 packets. And then let's say node 1 met node 2. Then at this point, node 1 will have 8 packets, no, 4 packets. Node 2 will have 4 packets. Node A, as before, will have retain its copies because it didn't hand over any. Maybe now A meets node 3, so A keeps 4 copies. Maybe node 2 meets 3 next, nothing changes. Why? Because they both have copies already. Okay. Maybe node 2 meets 5, and then A will keep 4, this will keep 4, node 2 will keep 2, 3 has 4, node 5 has 2 copies. Maybe node 5 meets node number 4, and then you can see what's happening. Okay, maybe 4 meets node 6. Okay, and why did 6 not get any copies is because it was met by node 4, and node 4 only had 1 copy. If it has 1 copy, it makes no more. Okay, so the only time you're allowed to hand over copies is if you have more than 1. And then maybe node 5 meets node 6, and same thing again. I should have picked a different one, but since I did, let's just do it anyway. Maybe node A meets 6. So now A will lose half of its copies. Okay, and then finally, let's just say, for the sake of argument, that 3 meets node B, and all of these numbers will kind of But basically at this point, what you're really doing is you have it delivered. Now, when I say it hands over 2 copies of the packet, we don't literally mean it does 2 transmissions. It just means it reduces its copy count by 2, gives the packet, and the other one's copy count increases by 2. So note that sharing K over 2 copies only requires transmitting 1 copy and updating counters. That's all it actually physically has to do.
Both the nodes already have the copy,
Then they do nothing. I thought I tried to include an example like that. Did I do that? Maybe this one, 2 to 3. So at this point, 2 and 3 both had copies, and after their encounter, nothing changes. Right? In this case, they didn't change also because they had the same number of copies, but even if this node had 2 copies, you had 4 copies, you still wouldn't change anything. So you only make a copy if the other node has got no copies at all. I think you could change that a little bit. It probably wouldn't affect the performance of the algorithm much, if at all. So what have we achieved by doing this is that, first of all, note total number of transmissions in the network is less than equal to the capital K, which is what you started with at the source node. See, because you never make more than this many copies at any given time, in the worst case, you end up with K nodes in the network, each of which has 1 copy, right? And so, in fact, K minus 1 is that upper bound in the total number of communications that might happen. So unlike flooding, if I have a 10,000 node network, a 1,000 node network, if my K was 16, I'll have at most 15 copies made in the network. And so with respect to the efficiency of flooding, this one intuitively is better. On the other hand, as I create more copies, the opportunities for the destination to meet somebody with a copy should increase, right? And so as K goes up, we are creating, if you will, a hybrid between wait and deliver and flooding. In particular, K equals 1 is wait and deliver. True. And K is infinity. In fact, it doesn't have to be as large as infinity. In fact, any number that well, you have to be careful. You want to make sure that everybody is able to deliver. This takes a little bit more thinking on my part, but certainly for large values of K, it's equivalent to flooding. It's a little tricky because the way the copies are made, if you end up with just 1 copy, then you can no longer, if you end up with just 1 copy, you can no longer copy, whereas flooding will always make copies, right? So K has to be large enough. In fact, you don't need it to be quite infinity. I'm just blanking on the top of my head. I think even like 2 to the n plus 1, where n is the number of nodes, might work. So let's just try that out for a second. I think I have time, yeah. So let's try n equals number of nodes. Is there any way in which you could end up with things are falling from the sky here? What's going on? It's really worrying. I hope this thing doesn't crash on my head. Oh, you think that's why it's dropping? I see. Maybe that's what it was. I'll try not to move this. Maybe I won't have that fall on my head. Okay, so I'm trying to think whether this will be enough for me to guarantee that I will never end up with just one copy at any node. So long as I can guarantee that, it'll behave like flooding. And my claim is I think this is enough, because at most you will make n copies. Each time you'll cut it by a factor of half. Yeah, so in fact, you don't even need n plus 1. I think even 2 to the n will do. But this will guarantee each node always has greater than 2 copies. Because every time you encounter someone, you would reduce your copy by a factor of 2. Right, would that be enough though? Yeah, or greater than equal to anyway. Yeah, so long as this is true, it will behaves exactly as flooding. So you've got this parameter k. We can have it as low as 2, we said, and we can have it as high as 2 to the n or 2 to the n plus 1. And as you vary that number, you go all the way from one extreme to the other, and you'll see that full trade-off. As you increase k, gives lower efficiency, because there's more transmissions that happen, but also lower latency, because it makes it more likely that you'll encounter the destination node sooner. And decreasing will have the opposite effect. So decreasing k increases efficiency, but also latency. Okay. So it gives you a way to kind of go between those two extremes. I want to mention very briefly, if I can, not to spend too much time on it, that we also at USC developed a protocol called BEWARE, which stands for back pressure with adaptive redundancy. And the basic idea was that you move packets between nodes only if, I and j, only if qi is bigger than or equal to qj, not bigger than equal, just bigger than qj, and if q's are small, then don't just move the packet, you actually make a copy. Then copy packets. So the point is that you don't always copy packets, you only copy packets when queues are small. The benefit of this approach is when the network is starting to get congested, if you have a lot of data in the network, which the previous schemes don't care about the total amount of data in the network, but if you have a lot of data in the network, then it becomes inefficient to be creating additional copies, which reduces your throughput. And so this back pressure with adaptive redundancy only makes copies if the queue sizes are below some threshold. And what we can show is that this gives same latency performance as schemes like spray and wait. So you can still do the spray and wait scheme in terms of how many copies you make, but gives higher throughput. So it sort of says, in addition to the throughput benefits of reducing the number of copies you make, you also choose when to make those copies only to times when the queues are not too full. If the queues are full because there's a lot of data in the network, there's a lot of congestion, then don't make copies. That's basically the idea. And it's been shown that that's a good scheme to kind of reduce the overall congestion in a delay-tolerant network as well. So let's talk a little bit about how do you model, so basically how to model and analyze the mechanisms for delay-tolerant networks or intermittently connected mobile networks. So DTN stands for delay-tolerant networks. So one way to think about this problem is, what if you have deterministic known encounters? Okay. What might that even look like, first of all? So what we sometimes do to think about this problem is to think about drawing a trellis diagram showing connectivity over time. Okay, so let's just say these are the nodes in our network. I can create this trellis in which the number of rows of nodes is how many nodes I have in the network, and I basically am creating as many spaces between them as time steps. So this is time 1, time 2, time 3, time 4, time 5, and so on. So what I'm trying to say is that maybe at time 1, when I say node 1 and 2 are in contact with each other, I put an edge between them. Maybe node 2 and 3 are in contact with each other, I put an edge between them. And for now, let's assume that these are bidirectional links. So there's a link between 2 and 3, there's a link between 3 and 2. Maybe at the next time step, nodes 5 and 4 were in contact with each other. Time 2 and 3, maybe these two nodes came into contact with each other. Maybe time 4, maybe node 1 met with node 5. And maybe at time 5, it was these two nodes meeting each other. So what this is saying is, it's kind of describing who met whom when, right? For convenience, we might also put edges between the same node over time. So basically, sort of implicit in this graph is there's always a way to communicate with yourself, or you can imagine this is a way of saying you're able to carry your data through. So in this trellis diagram, if I put arrows on the edges, so there's sort of an arrow going in the forward direction over time, that's causality. Okay, so all of these edges would be labeled with the direction. Okay, and so on. So what is the direction? Do we absolutely need it? I think it's helpful. If you follow from node 3, it can tell you all possible ways in which data from node 3 can get to other nodes in the network. So node 3 can hold on to the data till here and then hand it over to 2. Or it could hand it over to 2, 2 could carry it around, and so on. Or node 5 could hold the data and give it to 4, and in this case there's no way out of 4. Node 1 could give the data, hold on to the data and hand it over to 5 all the way here, and so on. Right? So it's basically showing you over time who can store the data, who can they hand it over to, and when. And all of the possible ways in which data could go through the network can be represented using the trellis diagram. So if you know the encounters in advance, right? So if the encounters are known in advance, you can construct this graph over all the known encounter times, and that in some sense is your network graph. You can then reason about connectivity deliverability, routing, delay, efficiency, etc. by studying this graph. Okay. You can compute the shortest possible way to get data from node 1 to node 5 by looking at this graph. It's just the shortest path routing over this graph. You can say, if I have a particular scheme like spray and wait, and I started at node 3 with 16 copies, how long would it take me to deliver the copy to the final destination? How much would be the total expense of doing it, and so on. So all of those questions can be answered by just studying this diagram. Okay. One comment I wanted to make that we didn't explicitly address before is, let's take this example we were giving about spray and wait. We said that at this point, node B would get the data. But if you look at the protocol would keep continuing to make copies of, each node would keep sending, half of its copies to any other node when they met. The point being that there is no guarantee that all of the nodes in the network know when the data has been delivered, right? Unlike in a traditional network, if somebody gets the message, maybe they can send back an ACK, it could even be flooded through the network or something. But here, there's no way for other nodes in the network to know that the data got delivered, okay? So it may happen in the worst case that even though the final destination got the data, you're still making a lot of copies in the network. And one way to deal with that is just throw up your hands and say, well, we couldn't help it. It's a distributed system. There's no way to get that information there. Or, so these are basically what sometimes gets referred to as the termination criterion. Even if destination gets the message, due to the distributed nature of ICMN, other nodes may continue to forward or make copies. Okay. Either do nothing about this. So basically it'll terminate when eventually the data gets to the point where only one node, each node has only one copy of it. Or you can set a timer. If you believe that the data was likely to reach the destination within time t, and you don't require the algorithm to keep running forever, then at time t you just terminate. If by then you have not delivered, you drop the packet. And finally, you could, in certain cases, send an Ack Flood to suppress further transmissions. But this may backfire depending on what system you have. Okay. An Ack Flood is basically the destination says, I got the acknowledgement. Oh, how could it backfire? Well, if you have 1,000 nodes and, your K value was set to 16, only 16 nodes actually participated in forwarding the message to get it to the destination. The destination gets it. It then does a flooding, or basically epidemic flooding of the acknowledgement message now over the whole network. Your acknowledgement overhead is higher than the data delivery overhead. So that's sort of a waste of resources. Basically, can you afford to flood an acknowledgement throughout the whole network? That's the question you might take into account. And how quickly will that acknowledgement flood even get there? What if the flood takes so long to get there that by the time everybody else is done doing what they were doing anyway? Right. So there's no way to speed up an Ack Flood over everything else. It's still subject to the same timeline.
Every node, if it maintains like the other nodes as their names with the most recent packet they've seen, and whether that packet has been delivered or not. So if you share that information,
so that you don't get any further, you could potentially think of some lower overhead way of trying to disseminate this information. But ultimately, whether that gets used or not depends on the forward route as well, right? The other scheme which might be fine is maybe the final destination is capable of, so basically there could be scenarios in which the transmission range of the destination is much larger than the transmission range of the other nodes. So for example, we work a lot with these low power devices. They can't transmit very far, but maybe the final destination has a very large power transmitter, so the Acks can be delivered for free or for very low cost to everybody in the network to say, I got the message, everybody stop your forwarding. So depending on the network that you have, the termination criterion might be different. So I wanted to mention that. Sorry, this is a little bit of a digression to catch back on a point I missed earlier, but my first kind of discussion here of the Trellis diagram was to address the question of how do you model and analyze DTN mechanisms. And it's saying that if I knew what the encounters were and when they happened, then I can draw this diagram, right? The problem is that because the mobility itself may be random, I may not be able to draw this graph because I don't know when they're going to meet in advance, okay? If I ran a simulation, on that simulation I could collect this data and I could run it for that run, but the next run it might be a completely different graph. So I end up with all of these sort of random trellises over which I'm trying to understand performance, and that can get rapidly difficult to analyze. And so in order to deal with that issue, we sometimes consider a very simple mobility model, or rather encounter model, to analyze ICMN protocols. Okay? And that model is simply called, and you'll see immediately why, the IID encounter model. Okay? So the idea of the IID encounter model is that at each time, so you have time is discrete, and that at each time, any pair of the n choose 2 pairs of nodes are selected at random to meet each other. So there's only one contact at each time. The contact is between a random pair of nodes. Okay? And it turns out that this model is powerful. It's simple on the one hand. On the other hand, it's powerful enough for us to say something meaningful about how many messages or what's the latency of flooding, how many messages does spray and wait take, and so on. So as an example of this, let's use this model, okay, and as an illustration. Let's use this model to compute the expected time to delivery for flooding. Okay. So what do I mean by this? Let's think about it first before we get into any math, and I'll continue it into the pre-taped lecture after this because we're running low on time here. But let's think about it first conceptually, what we're saying. So we begin the process, one node has the packet, okay? At each time I'm going to pick a random pair of nodes and I'm going to imagine an encounter between them. If one of those pairs has the packet and the other one does not, a copy is going to take place. That's what flooding will do. If neither of them has the packet, nothing will happen. If both of them have the packet, nothing will happen, right? So the only time something interesting will happen is if I pick a pair such that one of them has the packet and the other one does not. And when that happens, I make a copy. Now I go to the next time slot. I pick another pair of nodes at random. Depending on what has happened so far in time, some nodes have packets, some nodes don't. So when I pick these two nodes at random, they may have packets or they may not, or one of them might have it and one of them might not. Again, if one of them has a packet and the other one does not, a transfer will take place. I keep repeating this process. It's a random process. How long will it take me to get to the point where all of the nodes in my network, okay, have the packet? So I'm not just doing it, well, we could do it time to delivery, but probably actually simpler yet. I mean, time till all nodes get the packet. I guess what I'm saying is not delivering it to one particular destination. Let's just look at how long it takes for everybody to get the packet. You can then also derive how long it would take for one particular node to get the packet using a similar analysis, and I'll either comment on that or leave that as something to consider on your own. So what's the process really look like if you want to imagine this process? So it starts with one node having the packet. Okay. So imagine some description of the state of the network which says how many nodes have the packet. It starts with one node, and the process ends when exactly n nodes in the network get the packet, because there's n nodes in the network. At each time, you're able to advance the number of nodes that have the packet at most by one. Okay. So it's basically, think of it as a chain that only moves one step forward to the right, and it may not always move. So for example, when I only have one node in the network with a packet and I pick two nodes and neither of them has the packet, it's not going to change state for the network. So the time it's taking me to move from 1 to 2, this is a random time. Okay? So I can ask in expectation, how long will it take for me to go from the first node having the packet to having two nodes in the network having a packet? And the reason why it's not exactly one is that that first node that has the packet may not encounter anybody in the first time slot. It has to be picked up at some point. And until that pickup happens, we won't transfer even one. And similarly, at any given moment in time, if I have k nodes having the packet, how long will it take for me to have k plus 1 nodes have the packet? Let's call that tk to k plus 1. That's also a random time, right? And in this case, what we will need is that one of the k nodes that has the packet has to meet one of the n minus k nodes that does not have a packet, and only then will I move one more packet and move to the next state. Okay? And so finally, the expected time I'm interested in, right, total time to deliver to all nodes, is simply the summation from k to k plus 1, this random time for k starting from 1 till n minus 1. So if I add up all of these times in expectation, and it's the linearity of expectations, the expectation of these times is the summation of these expectations, that's the time I'm interested in. So if I derive an expression for the time to go from when I have k packets to k plus 1 packets, the expectation of that time will be, and summed over all of those, will give me the total time to deliver. Okay, so that's how we would do our analysis. So to analyze this, we construct a geometric random variable where, with some success probability p, it happens in one time step. How long does it take for it to happen? The expected time for that process, so if you construct some x, the expectation of x will be 1 over p, right? So if we can figure out the success probability, if you have k nodes have the packet, what's the probability that you will pick two nodes where one of them has the packet and the other one doesn't? That's going to be p. 1 over p will be the time of interest to us. Okay? So we'll do this in the 1 hour period that I have from 3 to 4. Just mention that again, 3 to 4 p.m. today, to be continued. And the class is actually in OHE 136. I forgot to mention that, I think. Okay, so in that session, I will complete this analysis and talk about the transport layer. And also talk a little bit more about the style of analysis, perhaps. Okay. All right, so we'll stop here for now.
This concludes EE 597 on Monday, August 1st, 2016.